Hi everyone. This is going to be a video lesson about limits involving infinity for calculus. So we've been talking about limits lately, and by now we should be pretty good at limits, both in terms of formulas and also in terms of graphs, and we also understand one-sided limits. So now we're going to look at what happens when infinity gets involved. So let's go ahead and get started. So I think you've probably noticed by now that a lot of times when we start a new topic, I like to start with a question to kind of motivate what we're going to be talking about. So I'm going to start with a question here. And it is, what is the limit of 1 over x squared as x goes to 0? All right, so what is this limit equal to? And we need to talk about this a little bit because it's going to be a different kind of limit. It's a little bit of a different kind of problem from what we've seen because this is a rational function, but 0 is not in the domain. So that means that the theorem that we had about just plugging in 0, it does not apply here because 0 is not in the domain. But also, there's not really any simplifying we can do. There's not really any factoring or simplifying or algebra that's going to help us. One thing that we could do is we could try to go back to looking at a table or a graph, because that's kind of how we started our discussion of limits in the first place, right? When we first started talking about limits, it was based on tables and graphs. So what you could do is you could try graphing this. Two websites that I like that work kind of like graphing calculators are symbolab.com. Another is desmos.com. I'll just say etc. I actually think in this case desmos.com is probably better in this case. But anyway, you could take a minute and try this. You could pause the video if you'd like and see if you can graph the function f of x equals 1 over x squared and try to investigate what happens as x approaches 0. What you should find is that the graph of this function it looks something like this. You know, if you use software, then you'll get probably a more accurate graph than what I'm doing here, but looks something like this. Here's 0. Here's the y-axis. Here's the x-axis. Okay. So we want to talk about what happens as x approaches 0. And since it's a limit without the one-sided notation, this means we're approaching from the left or the right. So how about this? When I approach from the left, what's happening? When I approach from the left, I'm going up this really steep curve. It's going up and up and up, and it looks like it's just going to go up and up and up forever. If I approach from the right side, I'm on this other part of the curve, and I'm going up here, which is also going up and up and up forever. I think what I'm going to say is that as x goes to 0, 1 over x squared gets bigger and bigger. Now, if you think back to our definition of limit, the limit equals L if we can get the function sufficiently close to L while x is arbitrarily close to A. Well, the problem here is there's no L. There's no number L that this is approaching. It's just getting larger and larger and larger. I'm going to say it does not approach a specific number. The function does not approach a specific number L. But it does approach positive infinity. When this thing keeps growing larger and larger, eventually it's going to be all the way, it's going to go off the top of my page, off the top of our screen, way up into the ceiling and above. And it's going to go up to 1,000, 1,000,000, 1,000,000,000, 1,000,000,000,000, and it's going to keep going. And that's what we mean when we say that it is approaching infinity. We write this as, we say the limit of 1 over x squared as x goes to 0 equals infinity. Now, I want to be clear about something. Infinity is not a number. It's not a number that we can plug into things. You don't just throw infinity around the same way that you would use like the number 8. It's different. Infinity is more of a concept. It's something that we can approach. And you might actually take issue with this. You might look at this and say, wait a second, shouldn't we technically be saying that this limit does not exist? Because we had a definition for limit. The definition said there has to be some number, capital L, and there is no number, capital L, to make this satisfy the definition of limit. So you might argue that this limit should not equal anything. It should just not exist. To that, I say, we use this new notation to describe the manner in which the limit fails to exist. Okay? So this can seem a little tricky at first, but basically, technically, if we're going back to our original definition of limit, you could say that this limit does not exist. However, it's kind of more specific or more preferred to write it this way, because this is telling us the limit does not exist because it's approaching infinity. There might be some other limit that doesn't exist because it approaches negative infinity. Or there might be some other limit that doesn't exist for a completely different reason, like a piecewise function with a sudden vertical jump. So there are different reasons why limits can fail to exist. This is one of the most common, and we use this notation to indicate that. We call this situation an infinite limit. Okay, the limit equals infinity. So if we were doing this in class, I would ask you, I'm going to ask you anyway, can you think of another name for this? Another name for this situation? This situation is also known as a vertical asymptote. It's a vertical asymptote on the graph. So sometimes we indicate that with like a dashed line. There is a vertical asymptote here on the y-axis that the graph is approaching, and it approaches that dashed line, but it never quite touches it. Now, let's get an actual definition for this stuff that we're talking about here. Because I'm saying things like this situation is known as an infinite limit, but let's actually have a definition for it. Okay? We are going to say the limit of f of x equals infinity as x approaches c. It means, let's be clear about what it means. F of x grows arbitrarily large by taking x sufficiently close to c. On either side, but not equal to c. I said something out loud a minute ago about negative infinity. It seems like if you took that graph, like that problem that we did above, and you took the graph and you just kind of flipped it upside down, everything would be approaching negative infinity instead. So that's another one that we should talk about. The limit of f of x equaling negative infinity as x approaches c. This means so if you think about it, now we're talking about a function that goes to like negative a million, negative a billion, negative a trillion. So how do we want to phrase this? Like, do you want to say that those numbers are small? If you say small, it kind of makes it sound like close to zero. Is negative trillion really like a small number? Here's how I'm going to say it. I'm going to say it means f of x is negative, but the absolute value of f of x grows arbitrarily large. And I like this definition using absolute value because this explains that we're talking about negative values, but the magnitude of them is very large. Like the absolute value of them is very large. So you take a number like negative 1 trillion. It's a negative number, but its absolute value is very large. And then you let that keep getting larger and larger. So we're heading off towards negative infinity. Now, all I'm going to say about the one-sided version, I'm going to say one-sided limits, or yeah, we'll say one-sided limits are defined similarly. For example, you could have a limit of f of x that equals infinity where you're doing x approaches c with the little plus sign. Okay, so I don't think we have to spell out every little word for that. We know what one-sided limits mean. Now we know what infinite limits are, and we're saying that you could have one-sided limits that go to infinity or negative infinity as well. So those are the definitions. Here's a question. Which of these situations do you think we can call vertical asymptotes? You know, is it the one going to infinity, the one going to negative infinity? What about the one-sided version? Would that still be called a vertical asymptote? So let's have a definition for that. I'm going to try to balance these pages on my desk. Definition. The vertical line, x equals c, is called a vertical asymptote. Let's underline that. Of f of x if at least one of the following is true. And it's going to be that the limit goes to infinity, or that the limit goes to negative infinity, or the one-sided version of these. The one-sided versions are also considered vertical asymptotes. So altogether, we're going to have 6 things here. The limit, the left-hand limit, the right-hand limit. If at least one of these happens, you say there's a vertical asymptote at x equals c. mean, sometimes you could have more than one of these happening at the same time, right? Because you could have the left-hand limit and the right-hand limit could both be going to infinity, and then you'd say the limit is going to infinity. So you could have like 3 of these happening all at once. Or you could just have one of them. You could just have a one-sided version. Maybe on the other side, something else is happening. Now, this section is called limits involving infinity. And what we just did is one type of limit involving infinity, but there's also another. So let's get a definition going. The other type of limit involving infinity is when a limit equals some number, but x is approaching infinity. This is different. This time, instead of x approaching c, this time the infinity symbol is showing up there. So this means f of x can be made. I'm just going straight for the definition this time. F of x can be made as close to L as we like. By taking as close to L as we like by taking x sufficiently large. There should also be a negative infinity version of this. All right, that got a little bit messy, but this is, let me see if I can fix that up a little bit. Some white out here. I just want to make sure this looks clear. X is going to negative infinity. This could equal L, and this means, well, it means almost the same thing. There's going to be one difference. So I'm going to put some quotation marks here and say some of the words of this definition are the same. F of x can be made as close to L as we like. What's different is this is by taking x to be less than 0 and absolute value of x sufficiently large. So this time we want x to approach negative infinity. So we want x to be negative and its absolute value is very large. Again, we're thinking of numbers like negative a trillion. It's definitely less than 0, and its absolute value is getting sufficiently large. I'll show you a couple of examples of this type of limit. Okay, so these types of limits. Example. One of them we've already seen today, actually. We could talk about this. When we drew the graph of 1 over x squared, and there was a vertical asymptote, didn't it also look like there was a horizontal asymptote? That's going to be what we look at when x goes to infinity. So let's think about what this equals. We'll draw the quick picture of it again. Okay, I don't really want to touch that x-axis, but I got really close to it. All right, so what is happening in this picture as x goes towards infinity? As x goes towards infinity, like here's 1 on the x-axis, here's 2, here's 3, but we want to go further and further and further to the right. Let x equal 1,000. Let x equal 1,000,000, 1,000,000,000,000. Keep going further than that. Keep going to the right. Now ask yourself, what's happening to the function? I would say it's approaching a height of 0. So I'm going to say this equals 0. I'll show you another example. How about the limit of e to the x as x goes to negative infinity. Do you remember what the graph of e to the x looks like? Hope so. A y-intercept of 1. Something like this. Y equals e to the x. So what's happening to this graph as x goes to negative infinity? Well, as x goes to negative infinity, this is going to the left. We're going, here's negative 1, negative 2, negative 3, right? And we want to go to negative 100, negative 9,000, and just keep going further and further to the left and ask ourselves, what's happening to this curve? It's getting lower and lower. It approaches the x-axis. It never quite gets there, but it approaches a height of 0. Underneath these, I'm going to say we call these a horizontal asymptote at y equals L. In this case, it would be at y equals 0. You know what? I've got an extra little question here. I'm going to ask you, what's the limit of e to the x as x goes to infinity? What do you think this is? Let me have you look at this for a second. We already have a graph of y equals e to the x on the page. The only difference between this is that, I already asked you this with x going to negative infinity, but now I have x going to positive infinity. So what do you think this equals? Well, if you think about it, x is going further and further to the right. We're going up this curve. We're going up and up and up and up. That's going to climb upward forever. So this actually equals infinity. The reason I wanted to show you that as kind of like an extra little problem is because I wanted to show you that it is possible to have a problem that has the infinity symbol in both places. X is approaching infinity, and e to the x is also approaching infinity. And that one would not be called a horizontal asymptote. It's only called a horizontal asymptote if there is some L, right? Like y equals L, such as 0 or some other finite number. So we've had a bunch of definitions, and what we'd like to do next is have some more rules and shortcuts for evaluating these types of limits. It would be especially nice if we could evaluate these sorts of limits without having to draw them every time. And I'm going to start by telling you a useful fact. And that is that the limit of 1 over x to the n as x goes to infinity always equals 0, and the limit of 1 over x to the n as x goes to negative infinity always equals 0 for any positive integer n. So we saw this happen earlier when n was 2. But now I'm saying it's actually true for any positive integer n. I would say the positive infinity version of it, the positive one, probably shows up more often in problems, but it's also useful to know that it also happens if x is going to negative infinity. X cubed. All of those equal 0. No further work required. We just say this is like a shortcut if you see one of those come up. And you might not get asked one of those just by itself, but where we're headed with this is you might see one of those show up in the middle of a larger problem, and then you'll know that that part of it is 0. Let's look at a bigger problem. Let's say we want to find the limit as x goes to infinity of this function. And let's try to do this without graphing. We'll talk about this together. This is just a polynomial, so it seems like a good representative problem. Maybe if we could answer this, maybe it would help shed some insight on how to answer polynomial questions. I mean, if x were approaching like 0 or some finite number, I know what we would do in that situation. But here, x is approaching infinity. We can't just plug in infinity like a number. What would you do? You would have infinity plus infinity minus 6. It wouldn't really make sense. So we're not going to do that. I'm going to show you a clever little idea. And the idea is we are going to factor out the biggest term, the front term. I want to call it the leading term. Technically, you could call it the leading term. The first thing here, the 2x cubed. I want to factor it out of this expression. Now, if you do that, you have a 2x cubed times something. And you might say, like, well, why did I factor out 2x cubed? Like, shouldn't I just factor out a 2? Everything here looks like it's a multiple of 2, so maybe that would have been nice. Right? 2, 4, 8, 6. But no, I'm actually factoring out 2x cubed. So out of the first piece, I get a 1. What do I get out of the second piece? How do you pull 2x cubed out of 4x squared? Well, we can do it. It's just that what we're left with is 4x squared over 2x cubed. How do you pull 2x cubed out of minus 8x? You have minus 8x over 2x cubed. And finally, the 6 will be over 2x cubed. And you can check that this line does equal the previous line. Just expand it, distribute this across the parentheses. You'll see these are both equal. What you might be wondering is, why are we doing that? That seems like a weird algebra step. We usually don't do that sort of thing. I'll show you why in just a moment. First things first, though, let's simplify this a little bit. We have things like 4 over 2, and we've got x squared over x cubed. We could definitely simplify this. This term simplifies to 2 over x. This is 4 over x squared, and this is 3 over x cubed. So there we simplified a bit. So I have a cool little trick to show you. As x goes to infinity, we could think about what happens to some of these parts. So 1 is still going to just stay as 1. What happens to 2 over x? As x goes to infinity, what happens to 2 over x? Well, we said up here that 1 over x would go to 0. 2 over x is also going to go to 0 because put a 2 in front of this. It doesn't change it, right? 2 times 0 is still 0. How about this? Minus 4 over x squared. Well, we said that the limit of 1 over x squared goes to 0. This is a 4 out front, but that's just going to be like a 4 times 0. So what happens to this whole thing here? As x goes to infinity, this part approaches 1. Because the 1 is still there, but the other parts become 0. And we wind up getting just this. And now we're thinking of just this piece. I mean, we could even like pull the 2 out. The 2 is a constant. You could pull that out front if you want. What do you think happens to x cubed as x goes to infinity? This whole thing is going to just be infinity. So we got rid of all the other pieces, and we were able to focus in on just the piece that mattered. And the nice thing is, this sort of reasoning, this kind of trick or this kind of reasoning always works for polynomials. And because it always works, we're going to call it a theorem. And we're going to call it a theorem. It's really going to function as a shortcut, and it's going to allow us to skip some of these steps in the future because we're going to say this kind of thing would always work out. So here's the theorem. If p of x equals, I want to write like a general polynomial. I don't know if we've done that this semester, but like I want to write a general looking polynomial, and I'm not going to make any assumptions on what its degree is. You know, it could be cubed, it could be something else. So we're going to write this as an x to the n, an minus 1, x to the n minus 1, plus ... We don't know how many terms it has, but it works its way down to a1x plus a0. In this situation, an is not equal to 0, and n is greater than or equal to 1. So this just says if p is a polynomial. Then, if p is a polynomial, then the limit as x goes to infinity of p of x equals, it winds up equaling the limit as x goes to infinity of just the first term. The rest of the terms wind up being insignificant. They don't affect the outcome. Furthermore, this always equals infinity or negative infinity. And we've got a little more to write for this theorem. And the limit as x goes to negative infinity of the polynomial, if you had a negative infinity problem, that is also going to equal the limit of just this term, and the outcome is also going to be infinity or negative infinity. So which one is it, infinity or negative infinity? Well, I'm going to say infinity or negative infinity depends on n and a sub n. It depends on the problem. In this problem, we had a 2x cubed. I mean, what if that 2 had been like a negative 2? That would have changed things, right? So that's what I mean when I say it depends on the problem. It depends on n and an. In this one, everything was positive. I'm also going to say, so that's the theorem, but I'm also going to say underneath it, the term an x to the n is called the leading term of p of x. I said that out loud a minute ago. Now we're putting it in our notes. So this theorem really works as a nice shortcut. It's telling us that polynomials always eventually head off towards infinity or negative infinity. This means that they never have horizontal asymptotes because it never equals some number L. So no horizontal asymptotes for polynomials. Also, this is kind of side note, but polynomials also never have vertical asymptotes. And that's because they're continuous everywhere, and they have a domain of all real numbers. Okay, this theorem is a shortcut for if you have a limit as x goes to infinity or negative infinity of a polynomial. We would like to have some rules or shortcuts or theorems about other types of functions as well. So the next type that we'll look at is, what about rational functions? Rational functions would be, limit x goes to infinity of like a polynomial over a polynomial. Like two different polynomials, maybe. What happens then? Now, for the polynomial version up above, we did like an example problem. I showed you how some things cancel. And then I said, that reasoning always works, so we can just say it as a theorem. For this one, I'm just going to go straight to the theorem. Okay? I'll go straight to the theorem. And then if we have time later, I might come back and do a problem without the theorem and kind of show you a little bit of the reasoning of why this works. But anyway, let's get this going. This is going to be f of x equals, we want to write out like a general rational function. So we want a polynomial over a polynomial. And we don't know what their degree is. They might be the same, they might not be. So we're going to use different letters up top and on the bottom. Different coefficients, but also different exponents. The only letters that's really are the same on the top and the bottom are going to be x. Polynomial in x and another polynomial in x. All right, we've got this. We've got am is not equal to 0, and bn is not equal to 0, and I guess we have to say m is greater than or equal to 1, n is greater than all that stuff. Then this is what you really want to know is what's the result if you have a rational function. Then the limit of f of x as x approaches infinity. Is there a nice shortcut? It turns out that it equals the limit as x goes to infinity of the leading term of the top divided by the leading term of the bottom. And similarly for the negative version, negative infinity version, same kind of thing. So this is also saying that the leading terms are kind of the only parts that really matter. Everything else, as x really grows and grows towards infinity or towards negative infinity, the other smaller parts of the polynomial just become insignificant and they get overwhelmed by the leading terms. So the theorem says this, and notice that this theorem does not assume that the polynomials are the same degree. Like the m up top and the n on the bottom. They might be the same or they might be different. This theorem has a big furthermore. Because it feels like so far the theorem has not really told us the full story. It says the limit equals this. Okay, well, now what do we do with this? Like, we're still stuck with this. So the furthermore is going to help us to finish answering this question. So furthermore, there are 3 possible cases for these limits. Case 1. The 3 cases are going to depend on how the degree of the numerator and the degree of the denominator compare to each other. We're going to say case 1, if m equals n. If the degree up top and degree on the bottom are the same, then the limit as x goes to infinity of f of x is equal to the limit as x goes to negative infinity of f of x. They're actually equal to each other. And they both equal am over bn. And the line y equals am over bn is a horizontal asymptote. am and bn are just constants. So this is giving us some kind of constant. You know, maybe it's 2 over 3, or maybe it's something like that. And we've found the limit, and we've also found that that is a horizontal asymptote. There's 3 cases. That first case is probably the most interesting one, to be honest, out of these 3. It might be the case that you see the most often. But we still need to talk about the other ones. So what other cases could there be? Well, there could be the case where m is smaller. In that case, the limit as x goes to infinity of f of x is equal to the limit as x goes to negative infinity of f of x, and they both equal 0. And the line y equals 0 is a horizontal asymptote. That's a nice case because that's a pretty easy one. As soon as you see m is less than n, the degree up top is less than the degree on the bottom. The reason that happens is because the degree up top is the smaller one. The degree on the bottom is large. So we've got that situation where the denominator is growing incredibly large. You have something like 1 over a billion, 1 over a trillion. You're getting really, really close to 0. That's the idea. And then finally, the only other case there could be is if m is greater than n. So the degree is now greater up top. Then each limit, when I say each limit, I mean the infinity one and the negative infinity one. Each of those will be infinity or negative infinity, depending on the function. You have to look at if things are positive or negative. And then there is no horizontal asymptote. It makes sense that we needed to have a case like this because some rational functions just don't have horizontal asymptotes. So they fall into case 3. Now, if this all looks familiar to you, it's because you may have seen this before either in an algebra class or in a pre-calculus class, because in those classes you probably talked about rational functions and asymptotes. And, you know, we talk about graphing them and finding asymptotes and all of that stuff, and you had 3 cases, and it was about the degree up top and degree on the bottom. What's different now is that we are saying all of this with this limit terminology. Because back in an algebra class or pre-calculus, you probably were not calling these things limits. But now we understand that limits are really the more precise way to talk about these concepts. Like when we say it looks like something is approaching an asymptote, that's kind of informal. Definition of the limit, that's rock solid. That's formal. Okay, how about some quick examples? Let's do some quick examples here of using this theorem. Quick examples. Let's say we want the limit as x goes to infinity of 3x squared minus x minus 2. I'm going to show you how fast it is to answer these, but I'm going to write 3 of them. So let me write all 3. There's 1. There's 2. And here's 3. And you could try these on your own if you'd like. If you would like to pause the video and try these, that's fine. Or you could just let me talk about them. Either way is fine. So, I'll give you a chance just so that you can write them. All right, they're all polynomial over polynomial. In the first case, the degree up top is 2. The degree on the bottom is 2. That means it's case 1. Case 1 says that we want to say the limit equals just the coefficient of the leading term up top over the coefficient of the leading term on the bottom. That's going to be this 3 over this 5. That those are the numbers that really matter, and this limit equals 3 over 5. And we're done. So this theorem is a massive shortcut for us. It tells us that we can just kind of read the answer from the problem. Off to the side, I'm just going to say, just so in case we're keeping track of this in our notes, this was case 1. But you don't have to write that. The second problem, the degree up top is 1, because that's just 5x, right? So the degree is 1. It's a 5x to the 1. And the degree on the bottom is 3. So we're falling into that case 2, where the degree up top is smaller. Case 2 tells us that the answer is 0. No further work is needed. You figure out what case it is, and you do whatever that case says. Case 3, or I should say problem 3. Problem 3 has degree 3 up top, degree 1 on the bottom. Definitely is case 3 because the degree up top is larger. So this equals infinity or negative infinity. I'm going to just take a quick look. X is going to positive infinity. The x cubed up top is positive. 5x on the bottom is positive. Everything is positive, so we just have positive infinity is the answer. So case 3. So that was a quick examples of one of each type. Let me give you a couple of these to try. They're pretty fast. So I'm going to ask you to evaluate. So I'm going to write 3 of these, so you could wait till I write all 3 of them, and I'm going to ask you to try all 3. So limit as x goes to infinity of 10x cubed plus 5x over 2x cubed minus 5x squared. Part B, limit x goes to infinity of parentheses 5 plus x minus 2 over x squared plus 3. And part C, limit x goes to infinity, x plus x squared plus x cubed plus x to the fourth divided by 3x to the fourth minus x squared plus 10. So I'd like you to try all of these. This would be a good spot to pause the video, take a minute, and give this a try. All right, so let's talk about these. All right, so we figure out what case these fall into, and the first one looks like the degree up top is 3, degree on the bottom is 3. So this is a case 1 situation, and I'm looking at this 10 over 2, and I'm thinking, you know, the reason I chose the 10 is because it's attached to the largest power of x. I chose the 2 because it's attached to the largest power of x. So this is 10 over 2. But don't stop there. Simplify it. Your answer should be 5. If you get something like 10 over 2, you should simplify that answer. The next one, what do we have to do here? So, is this a rational function? I mean, there's like a 5 plus in front of it. Here's what I think we should do. Let's separate this. Let's deal with the 5, and let's deal with this other stuff. You know, because we have rules about limits that say you can split this up like this. All right, that way we can deal with the 5 and the other stuff separately. So what do you think? What's the limit of 5 as x goes to infinity? Well, as x goes to infinity, the constant 5 is still just going to be 5. It's not going anywhere. There's no x's involved. So that's 5. This stuff here, the degree up top is smaller. So as x goes to infinity, this whole thing goes to 2. Or I'm sorry, I said 2. I don't know why I said that. This goes to 0, which is what I wrote. 5 plus 0, this equals 5. That's a coincidence that part A and part B have the same answer. I guess another way you might have been able to do part B is if you had if you decided you wanted to find a common denominator and merge these into one fraction, you could probably do that. But I think what we did here was easier. And finally, part C, what's the degree up top? Well, I've got an x here, but the degree up top is 4 because the x to the fourth is over here, and down on the bottom we have x to the fourth. So actually, let's circle the 4s. 4 and 4. This is case 1, right? Case 1 because the degree up top and degree on the bottom are both 4. So we want to take the coefficient in front of x to the fourth. So what coefficient is here? We have to imagine there being a 1 here. I just wrote that 1 in. But we have 1 copy of x to the fourth. We have 3 copies of x to the fourth on the bottom. So altogether, I'm going to say this equals 1 over 3, 1/3. So what I was hoping you would notice with part C is that the leading term might not always be the one that's furthest to the left. The leading term is the one that has the highest power of x. That's the most significant, impactful part of that polynomial. X to the fourth is much, much larger than x to the third or second or first. All right, so we made it to the end of the lesson on limits involving infinity. We basically saw 2 types of limits involving infinity, and visually they kind of correspond to vertical asymptotes or horizontal asymptotes, and we solved a couple different types of problems. So that is actually going to be in a certain sense, that's going to be the end of our discussion of limits, because in the next video, we're going to start on a new topic. However, we are still going to need limits for what we're doing going forward. We're just going to be using them in a certain way. So I want to say that from this point forward, the next few videos that we have and the next few lessons that we have are very important for calculus. We're going to start talking about the derivative, and that's going to be the topic that covers most of the semester. So you don't want to miss the intro to the derivative. So the next few videos are very important. Okay, so hope everyone is doing well, and I will say take care, and I'll see you soon. Bye.